Now, in the following video clip, we're going to discuss the second topic that we started on Thursday. It's called unit impulse response. Unit impulse response is a special zero-state response. Special zero-state response. Okay, so keep this in mind. The special thing about it is your input, because for zero-state response, everything is caused by your external input, and all initial conditions are zero. So the special thing here will be a special input. This special input is actually the simplest input signal we can imagine. The unit impulse function delta of t. Meaning at time 0, you're going to flick the system and look at how it responds. So give a quick flick, quick push, quick nudge. Okay. And systems usually will respond, will move a little bit like something push you, and you're gonna move a little bit. So unit impulse response is actually see how the system will respond to such a short time strong input. Now, later on what we will see is the unit impulse response can be used as a building block to construct the response, the zero-state response to any arbitrary input signal. So let's see how can we find the unit impulse response. Since the input is a special signal, our delta function, we give a special name to the corresponding output. We call it h of t. So whenever you see h of t, it's just the mathematical symbol we assign to represent the unit impulse response. Okay. Now, if you want to solve the unit impulse response, you can do the hardcore math. And if you're interested, you can read the appendix to chapter 2. It gives the derivation of how h of t can be calculated. What we're going to do here is to directly give the solution and walk you through the steps through a couple of examples to illustrate the process to eventually obtain this h of t. Now, later on in the semester, especially in chapter 6, we're going to learn a mathematical tool called the Laplace transform, which will provide us another way, actually will be a much easier way to obtain h of t. But at this point, let's do the mathematical procedure we're going to discuss next. So it was proved, if you're interested, you can read the appendix to this chapter, that h of t can be obtained and can be expressed in the following form. Actually, it contains two terms. The first term is Bn multiplied by delta t, where Bn, as we discussed earlier, is the coefficient of the differential equation corresponding to the nth derivative of the impulse signal. Remember, it has to be the nth derivative. Let's come back. And the second term is a little bit tricky. It contains this P of D. We'll explain what P of D is. P of D will be applied to Yn of t, and we'll discuss what Yn of t is. And the entire thing we multiplied by u of t, which is our unit step signal. So what is P of D? Now, P of D is a polynomial of D, which comes from our differential equation. And what you're going to do is to apply a similar procedure as when you try to find the characteristic equation, but now the tricks will be on the right-hand side, on the impulse signal side. And whenever you see a derivative, it will be replaced by a d. And d, this capital D, is called a differentiation operator. So if we write dy, it means we're taking the derivative of signal y with respect to t once. If we write d squared of y times y, that means we're taking the second derivative of the signal with respect to time. If let's say I'm doing dn of times y, that means I'm taking the nth derivative. So, as you can see, now p of d, this polynomial actually represents exactly the polynomial or the differential equation on the right hand side. Right here. Now, let's move down again. And later on, we'll use an example to illustrate how this can be done. So if p of d is like this, meaning each one of them has to be applied to this yn of t. So if you want to further expand it, it should look like this. So you have this bn of delta t, and you have to apply each term, so it will be bn times, take the nth derivative of dn y dtn, and the second derivative, the n minus 1 derivative of this yn dt, n minus 1, plus all of them, so b1 of dyn dt plus b0 of yn itself, and this will be multiplied by u of t. Now, here's still something that hasn't been solved yet. What is this yn of t? This is a special signal that is required to be found when trying to solve for the unit impulse response. And the way to calculate it is very similar to the zero input response calculation. Now, to find yn of t, you also need to find the characteristic equation, as we have done before. Second, you need to solve it to find the roots, meaning all the lambdas, lambda 1 up to lambda n. And then, at the third step, assuming all these roots are distinct, yn will take a form as a bunch of the sum of a bunch of exponential signals coming from these lambdas. And of course, here you have a new set of coefficients, those b's. So to find the values of those bi's, b1 up to bn's, a special set of initial condition will be used. The special set of initial condition will look like this. We'll start from yn of 0, meaning you make all t equal to 0, so it will be b1, b2, all the way up to bn. You set it to 0, and then you take the first derivative, that's another initial condition, assuming now n is larger than 2. So when you take the derivative, will be and evaluate it as t equal to 0, you will have lambda 1 times b1 plus lambda 2 b2 when you take the derivative and let t equal to 0. And you can do this since you have a total of n unknowns, you need a total of n equations. So this will go all the way back to dn minus 1 dt n minus 1 of y. And that's evaluated at t equal to 0. So what this will be equal to, apparently you need to take the nth derivative. When you take the nth derivative, lambda 1 will come over n minus 1 times, multiplied by b1. Lambda 2 will come up n minus 1 times. Let me redo this. N minus 1 times b2 plus everything, and lastly will belong to n to the n minus 1 bn. Now, for the very last initial condition, instead of setting this to zeros, you want to set this to 1. Okay. Don't ask me why this has to be 1 or the other has to be 0. You need to read all the appendix, the math, to figure out why. Yeah. But so as I said, here I'm just giving the procedure how to obtain it. And after all of this, you'll be able to solve for all the b's, and when you have all the b's, take it back to yn, and then take yn back to all the derivative calculations here, and make sure you take the correct derivatives. And that'll be it. So as I mentioned, a common mistake is so I'll write it in a different color. So a common mistake is after you solve for yn of t, you will directly use yn of t in this equation, which in general is not correct, because you forgot to take the derivatives that's required up here, which comes from this PD polynomial of this differential or differentiation operators. So make sure that you have this included in your solution. Now, this is a long procedure, so let's use a couple of examples to illustrate how this can be done. And we're going to do the examples in the next section of the video.